Hi, welcome to the Signal Path. In this episode, I got another repair for you guys. This is an Agilent N1912A. This is a P-Series Power Meter. Now, unlike the EPM series Power Meter, this one offers much more advanced functions, and it actually has 30 megahertz of analysis window bandwidth, which would allow you to do peak detection and burst detection and all kind of fancy plotting when it is connected to the appropriate power sensor that supports those functions. And so you can see the connector type is quite different from the EPM series. And I've done a repair on the EPM series power meter as well in the past. It's a much more expensive, much fancier connector. It has two internal coax. It's a hybrid type of connector, and just by the look of it you can imagine it's quite a bit more expensive, and the sensors are also a bit more expensive. And I do happen to have a cable that converts this to a traditional power sensor, so it's nice that it still works with those type of power sensor. It also has Ethernet, USB, as well as GPIB in the back. Pretty advanced unit, and these can be really expensive when they're working. So this one actually kind of works, and it has an unusual problem, and I wanted to show you what happens. It's a little bit difficult to replicate. Sometimes it happens, sometimes it doesn't happen, but I'm going to turn it on, and I'm going to show you when it boots up so we can catch that problem and see what we can do with it. So here we are. This is what we get. This is the screen we expect to get, and right now no sensors are connected, so it's fine, and I can run, for example, a self-test on it. I've tried that, and it passes. It doesn't report any problems. But once it runs for a while, the LCD screen gets totally messed up, and you will see it will begin to crash, and it will begin to create vertical lines, and then it will just become all jarbled up. And I think that means that something is wrong, either with the processor or with the LCD unit, or some other problem perhaps in the power distribution. Sometimes when you underdrive or under voltage some LCD screens, it could cause that kind of problem. So it could be any of those, and I have a few ways of diagnosing and figuring out if one of those is the issue. So right now, if I let it run for a while, nothing much actually happens until maybe about 5 or 10 minutes before the screen begins to fail, and it's repeatable each time when I turn it on. After the same amount of time this happens. This means that it is obviously thermally related, so it could be a thermal problem of one of the components. And interestingly enough, and I'll show you, and the reason why I think it could be a power supply problem is that when I connect the sensor to it, it happens faster, it happens earlier, and that could mean that because this block here has to then power the power sensor, which means there's more strain on the power sensor, more on the power supply internally in the unit, and that could be one of the reasons why this happens. So let's wait a little bit, see if we can replicate that. And I want to also see if I can continue communicating with the unit and get data from it while the screen is crashing by using the USB port, and that would mean that the problem is just on the LCD and has nothing to do with the main processor, and the unit is actually working in the background, and this is just the artifact of the LCD failing. So we can find out all of these things by doing a couple of experiments. Of course, first thing first, I have a cable right here which plugs into this, and look at just how fancy this cable is. I'm not sure who manufactures these connectors, but by the look of it, I'd have to guess either Japanese or German. So yeah, pretty expensive for sure. And I have this power sensor here, so we're going to go ahead and connect it to this. This is a 26.5 gigahertz power sensor, so we're going to go ahead and plug it in. If I plug in, this is the old style connector, as you can see. Let's go ahead and try it out. As soon as I plug it in, it's going to tell me minus 24 dBm. Obviously, hasn't been zeroed and it hasn't been called, so it's just giving me the lowest number it can give. Once I zero it and cal it, then it will be very accurate. In fact, I did a measurement with it and it's extremely accurate, so the issue is not with the measurement. So let's wait a little bit and see if we can replicate that failure mode again. And here we are. This is the failure point that I was talking about. So as you can see, this obviously is unusable, and we're still connected, but let me try and disconnect the sensor and see if I remove the burden of the powering the sensor if anything changes. Let's go, and here we go. See, as soon as I remove it, it partially recovers, and if I were to go and plug it back in, it breaks again. So that leads me to believe that indeed it does have some kind of a power problem, some kind of a voltage problem maybe, and that's causing this communication problem between these two sections of the instrument. So one other test I want to do is I want to quickly try out and see if it is still working in the background through the USB port while it is in this condition, and if they verify that also, and then we can then jump quickly to taking it apart, taking a look and see what's going on inside. Well, an annoying thing happened. The problem went away, and so now there's no point testing it through the USB. I tried it right now. Of course, it works right now. But yeah, I can't get the screen flickering to start again. So I guess there's only one thing to do. Just actually take it apart, measure the power supplies, and see if we can recreate this problem by creating some current draw or something, and see if we can cause it to fail again. All right, let's give this guy a try. So I already opened the screws on the back side, and it should come off. Oh, looks like it's connected at the top to something. Oh, it doesn't open in this direction. Gotta flip it. Oop, there we go. Let's see what we got here. And and there we go. And yeah, it's ridiculously complicated. Yikes. I'm in a bad position here behind the camera. But very interesting. It looks like this got completely different modules for different things. It's a really modular design, and some aspects of it seems a little bit overly complicated. So this is clearly for one of the channels, and this is another channel. So this can be configured in either one or two channels, which I suspect then they simply remove at the processing board. That's not necessary. And there's a lot of connectors that are unused. You know, here there are connectors unused. This might be a programming connector. And this board over here seems to house all the IOs. So the serial port, Ethernet, and USB are connected to this board. And over here we have the LCD module connected, but that looks like it goes to the motherboard at the back, and the motherboard is most likely the main processor. And here we have the power supply connected from over here down to the main motherboard there. Nice input connector, many earth. Look at that, there's just so much earth connection. So this top part here has a chassis, the completely metallic there, aluminum piece there, and then there's an earth connection to it here, there's an earth connection to it there. There is the power supply line voltage going in, the power supply module totally separate on top here, and then going with these many different connectors that are going into here. So really a lot of custom parts and a lot of attention to details there. A fan over here, which when you close it up, will blow across the power supply. Looks good otherwise. These two ribbon cables down here go to the front expansive connectors, the hybrid connectors, and they go directly into the motherboard. There's a couple of RF signals here, and they're obviously coming from the two RF connectors onto the connectors in the front. So there's 4 of them. That's 1, 2, 3, 4. Those are the hybrid coaxial centers of these connectors in the front going into the main motherboard. And there are some labels there, yeah, channel A, channel B, plus and minus, so there's actually differential. Interesting, differentially individually isolated. Quite a lot of attention to details for making sure that it is well noise isolated and interference isolated. Quite nice. And yeah, this is for power there for these two cables over here. This module over here is the reference generator. This is what generates the 50 megahertz 0 dBm reference for calibrating the different modules, and here is the LCD connector. I think that is it. No, I take that back. Sorry, this is the keyboard. This ribbon cable here goes to the front panel over here, which is where the keyboard is. The LCD module is contained within here. I don't think the keys are a problem, but I do see this is actually not very sturdy, so I'm gonna have to remove that and reconnect it just to make sure that it is nicely sitting in there. So yeah, looks reasonable. This is control signals for the reference generator. Nothing unusual other than that. So the first thing to do is to see if there is anywhere over here where there are labels on what kind of power supply voltages and everything else to expect. And then we can go from that and do some measurements and see if those power supply voltages are correct. That should be my first guess. Here we go. The instrument is powered on now and the screen looks fine. There are lots of blinking LEDs all over the place on this. Some diagnostic LEDs on the two modules, which are doing some symmetric activity there. They're working anyway, so that's the match, which is nice. There are some plus 5 volts and 2.5 volt references and so on labeled there, and a couple of LEDs that are not labeled. So that would be a pretty good place to start and to start measuring them, and we can see if those voltages are within tolerances of the instrument. Okay, some simple measurements. Now I assume that the chassis here is earth ground. It's also ground of the entire system. So let me find a nice place to connect this to. I suspect the aluminum here should be okay. So let's see if we see. So there's a 5 volt marked on this carrier board. Let's measure that first. 4.97, that's pretty good. I would say that's pretty close. And this one is 5. So interesting, you can see by the proximity of this particular carrier board to the power supply, there's a slight change in the voltage, or perhaps some variation within the regulators on here, if the regulators are on here. If the regulators are on the other board, then that would make sense. Let's do some measurements on the plus 5 volt here. There's a test point for that. 5 volt, no problem. And there's a 2.5 volt reference here. 2.5 volt, that's good. So the power supply voltage is appearing, at least the 5 volt, the digital, the logic looks good. So the question is this problem simply because the display is not sitting well, some connection is not being made very well, and it requires it to be disassembled and reassembled. Now, the screen is still okay. It's not doing that thing that it was doing. So we'll have to wait and see if that problem comes up and then do some measurement. I'm going to also try doing some measurements on the LCD screen itself, see if I find anything that would be of any interest. So here is something interesting. I'm just going to wiggle the connector that is connecting to the LCD screen from the back of the unit. And look, see that? By shaking it, I can make it go, there you go, I can make it go crazy. So interesting. So this is a connector issue most likely. That's kind of boring, but nonetheless, it's worth investigating. So either the cable is bad, or the connection to the motherboard is bad, like a cold solder joint, where we can re-solder the connector down and see if that fixes the problem. So next step is to take it apart further and investigate the connector a little bit more carefully. All right, here we are into the disassembly process, and pretty nice to see the structure. Just look at how complicated these things are. Look how many connections there are between the boards, and it's just crazy. A lot of data going back and forth, and I'm not going to take this off, but there's a ton of components, a lot of ASICs underneath there. You can see by just a footprint, a lot of BGAs. And I know maybe we can peel a little bit of it off and I can find out what's underneath, but it's probably some kind of an FPGA. For sure, this is an FPGA in the back, and there may be data converters and so on. But yeah, pretty cool to see that, some memory in the back for sure. And these modules are capable of analyzing the burst and the intermittent powers and detectors that I was talking about earlier in the video. So I took this off so I can have access to this cable here, and this is the front module. It's really fully contained, and it has one interface to the main board. The CCFL backlight is here. You can see just so much attention to detail. Every little tiny thing here has been thought out. This instrument, I believe, is made in Germany, which explains the meticulous nature of the way it is put together. And so let's take a look and see what's going on with this cable. Now, this cable from this side comes off the front, which is nice, but then the other side is got a fixed connection to the motherboard, which is, why did they do that? I don't understand. They've gone through the trouble of having everything else removable, and all of a sudden this one connector is not removable, and that's quite annoying. I wonder if there's a way. If I had this particular socket, I would go and replace it, but I don't, and I don't have the patience to wait for one and order one. So I just want to see if I can get this thing back to working. So this definitely, the problem is here. Now the question is, do I want to take everything out and unsolder or resolder this, or we can just find a problem by looking at it closely and see which of these connections is the issue. All right, check out this connection here. So this is the back of the board. I took the motherboard out. We're looking at the corner where the cable that is suspect connects to the motherboard. And if you look, you can clearly see there's a lot of solder flux around, and you can see that this has very uneven soldering and clearly done by hand after the board has been reflown. And the reason, I don't think I can focus that much. Come on, refocus there. So the reason this is done afterwards is because obviously there is no connector, so they couldn't reflow it with the plastic afterwards. So they had to attach it as a separate step, which is really kind of silly, given that it would be so easy to put a connector. There are so many connectors in the system. Just add one more. And the silly thing is that they've done, they have similar situations here. You can see that they have connectors, everything's done properly, and then all of a sudden this one connection in the entire system is done completely poorly. And of course, that's the failure point. So what I'm going to do is I'm going to clean this up. I'm going to run the solder all over everything, make sure everything reflowed nicely, and then clean it again. And I'm going to even cut the cable and reattach it to the pins that are there, and basically repress it and re-crimp it essentially manually. It's a little risky, but I think it's necessary to make sure that it works correctly. So I think I'm going to take the cable out first, re-crimp it, and then rerun this so that I don't disturb the solder again. But Yeah, kind of disappointed by such a simple oversight here, but let's see if this fixes the issue. All right, here we go. So I took this much of the cable off. That was, you can see the holes on this cable from where the part was crimped to that connector. Cut it off. I re-crimped it manually, one little pin at a time, and I reflow and restarted all the pins again. So now when I shake the cable, you can see, and I can shake it quite vigorously, nothing happens. It seems pretty stable there. So that's a good sign. And let's put it all back together, put it on the bench, and let's run it for 30 minutes or so, connect the sensor to it, do a couple of measurements, and see if it stays this way. Okay, let's do some quick measurements. So I'm going to go ahead and zero the channel, zero channel A. And this is going to create a reference of the lowest possible value coming from the power sensor. By the way, go and watch my repair of the EMP where I tear apart one of these power sensors and go into details on how they actually work. It's very interesting seeing the components under the microscope and the fundamental principle of operation is pretty fascinating stuff. So there it is there. We can now go ahead and calibrate it as well. Let's calibrate channel A there. And that's going to put a 0 dBm 50 megahertz tone directly into the sensor and cal it out, and now it's called and zeroed. So now we need to measure something and see how accurate, for example, the power generation is. And there's a couple of things we can try. Let me see here. For example, I can go ahead and try this guy, the Tektronix TSG 4106A. I just turn it on, and we're going to try and see how accurately it produces the kind of signals it's supposed to. So when I set it to 0 dBm, for example, and that the power sensor goes to 26.5 gigahertz. So it's not a problem doing that, and it's been on now for some time, and it's going to be continuing on. And let's see what happens when that thing boots up. Here we go. I connected the sensor to the TSG. Now remember that the reference plane of the measurement from the TSG is at the edge of the type N connector. We have one additional connector there because my power sensor is type K connector, and so there's going to be a tiny difference from that one connector, but that shouldn't matter too much. So let's go ahead. Frequency, let's select 1 gigahertz, and let's set the amplitude to 0 dBm. And where is dBm here? Where is 0 dBm? There it is. And I can go ahead and enable the RF port. There it is, and check it out. Right over here, we see minus 0.07. Now keep in mind that the correction factor here is set to 100%, whereas in reality, the correction factor for the sensor at around 1 gigahertz is 99.3%. So it's actually really close. It's quite impressive. The power coming out directly from the Tektronix TSG seems to be very accurate. So let's set up somewhat higher frequencies. Let's say go up to 6 gigahertz, and the correction factor is 97.9 for the power sensor at that frequency. Let's go 6 gigahertz. Let's see, frequency is 6 gigahertz, and now we see minus 0.78. So we have a slightly higher correction factor, and we have a little bit loss in the connector, but it still is seems pretty good. Let's look at the accuracy and in steps. So I'm going to go under the amplitude, and I'm going to go down by 1 dBm exactly. See, minus 1 dBm, 2 dBm. Look at how accurate it is. It's very good. Yep, minus 5 dBm. I would say that's pretty good. Let's go to minus 10. Look at that. That's exactly 10 dBm. And we can go to minus 20. And now it's a little bit less than minus 20. And remember, this power sensor only goes to minus 30 dBm. So if I go to minus 30 dBm here, this measurement is, even though it is essentially correct, and it's very accurate actually, it's not really reliable. And you shouldn't really be using at such an edge of its performance. But anyway, I mean, technically speaking, I guess it's okay. Yeah, it looks pretty good. I have to say I'm pretty happy with it. Let's set it back to 0 dBm. And let's set the frequency to 10 megahertz. So very low frequency now. 10 megahertz 0 dBm, and you can see it's minus 0.18. I don't have the correction factor for this particular sensor. Actually, this is beyond the specification of the sensor because I think the sensor starts at 50 meg. So let's set it to 50 megahertz. 50 megahertz 0 dBm. It's really close. It's pretty amazing. Yeah, I'm quite happy with that. So you can see the power coming out of the TSG 4106A from Tektronix is very good, and I'm pretty happy with it. And so far, this has been like this for some time, and it just doesn't seem to change anymore. So I would call that a repair. I know, not really much of a repair, really. I mean, all we did was fix the cable, but this is a good example of how a design can be 99% perfect in terms of how they chose to connect things together, and that 1%, that one little decision not to put a connector there, just completely messed it up. I noticed that the vertical profile at that point was very short. Maybe that was one of the reasons why they didn't put a connector, because they didn't have the clearance, but they could have put a horizontal connector. It didn't have to be a vertical one. So yeah, anyway, but you can see how you can totally kill, a pretty expensive instrument, but it seems to be working. And if I unplug this and put it on channel B, it should get detected. There it is, and of course it's not zeroed on CALD on channel B, so the value is off. But it is working, and quite nicely too. There it is. Yeah, very good. Pretty happy with it. I hope you liked this so-called repair video. I hope you enjoyed it. It's a pretty quick one, and but nonetheless, I hope you enjoyed looking inside the instrument and seeing an unusual failure in this. See you next time.